In January, an article came out in Nature Aging from Griffin et al. And her collaborators. And they introduced a new technique that they called time-seq that claims to reduce the cost of epigenetic testing by up to 100-fold. This study absolutely caught our attention. There are other studies, there are other technologies out there, but because this one kind of put the stake in the ground so firmly around this, I thought it was worth discussing, and discussing with the right people. So on this call with me, I have two experts in the area of genetics and epigenetics, Raymond McCauley and Miten Jain. Raymond, would you introduce yourself briefly and then turn it over to Miten to do the same?
Sure. And hey, Tom, and hey, Miten, it's great to be here with you guys. So I'm Raymond McCauley. I'm a scientist who works in the fields of genomics, materials, microbiology, biotechnology in general, and I've been doing work with DNA since the 1990s and was part of the team at Illumina that pioneered next generation sequencing for DNA. And since then, I've been involved with Singularity University as the chair for their biotechnology track and digital biology. And I'm the co-founder of several different companies, some successful, some not as much, and have been involved probably more recently for the last 5 or 10 years with shepherding companies, advising them, and investing in them in the biotechnology and especially the genetic testing space.
Thanks, Raymond.
Thank you, Raymond. Thank you, Tom. Great to be here. Hopefully, I can add some value. I think there's a lot of resource and expertise with Tom and Raymond. So I'm Miten. I am a professor of bioengineering, physics, and computer science here at Northeastern University. I also serve as the CSO at HLE. And my expertise comes from the nanopore technology and development platform. I was a graduate student in the nanopore group at UC Santa Cruz. Our group invented the technology, our group, the Royal We. I like developing technologies that intersect between genomics, computer science, and biological applications. In our group here at Northeastern and our group in Santa Cruz, we do a lot of development of applications that focus on how can we leverage the expertise and technology that we have and that's emerging from various colleagues in the domains to take DNA, RNA, and protein and other analyte informations to understand human health, make better tools for precision medicine, and ultimately with the goal of helping understand better on disease models and improving clinical applications. So what we are going to discuss is definitely of a huge potential and application. So looking forward to it.
Great. So as I mentioned, the right team indeed to discuss this. I'll also, just for full information here, we're all affiliated with a company called Human Life Expectancy, Inc. I'm the CEO. Raymond and Miten have been working with me on this for quite some time now, and we've become fast pals over the years, tracking epigenetics, its prospects for humanity, as well as insurance and other business opportunities. So, all of that done, let's get into it. Guys, what did you think of this study?
I think it's a pretty neat paper, and it's interesting. It's tracking work that this group has been doing for 3 or 4 years, and you can tell they are thinking about this the way we're thinking about this, that epigenetics and biological clocks are super interesting for a bunch of reasons, because they can give insight into groups and individuals, because they can do it in a way that some simple other kinds of phenotypic tests, blood tests and such, don't really give you the detail, that they are better than just genetic tests because you can go ahead and stack on a lot of information about what is happening in a person's life, not just the genes that they're born with. And they are trying really hard to make something that would let more people access this. And so I love that. I laud the direction behind it, and I think they have some pretty cool techniques.
I echo Raymond that the group, because they are veterans in the field. I mean, David Sinclair is not an unknown name to anyone in the field of aging and epigenetic clocks. So the idea behind the paper is very nice. We've all known, and it's a semi or if not completely established fact that there are tissue and cell specific signatures with epigenetic marks. biological clock associations and the patterns of aging and hallmarks and so on and so forth. And there's always an aspect of what is the right amount of information or the minimum amount of information that you need, which is something that this group has been working on for years. This is a very interesting take to combine that with how to make technology accessible. So, as Tom started the discussion with the question, how cheap can it be? And part of it is not just a race to the bottom, but also the cheaper it is, the more accessible it will be. Quite likely, consumerism drives the economy in that context. So the method that they developed, coupled with what they did in animal models and the extension to human, it's very both encouraging and exciting as a scientist and as an application.
That's great. So I am not the scientist that both of you are, so I'm delighted to be outnumbered by you and guided by by your knowledge of this. But upon my reading, the most revolutionary thing about it was truly the magnitude of the potential cost reduction. So if I understand right, what these guys are doing, the way they get their tests to be so much cheaper, is a combination of, I think, three things I'm hearing. One of them is kind of scope, how or long read versus short read. You can test for everything, look at all the CPGs, you can do whole genome sequencing, and that's going to cost you a lot of money. Or you can say, no, we know darn well what we're looking for. We're looking for these specific CPGs, and it's maybe these 100 or these 1,000. And that's a huge savings to be able to just reduce the scope. So that's one factor. Do I understand that roughly right?
Yeah, that's a nice way to put
it. That's a good way to put it.
All right, cool. The other one is volume. Right? The higher the volume you do, of course, the lower the cost per unit when you have fixed costs in machines and other thing like that. And I don't mean to put that short shrift, because that is a big, big, big deal. And that is one of the reasons why ultimately in insurance, where there's high volume, the cost can be extremely low. But then there's this other thing called multiplexing. Can both of you explain that a little bit more? What exactly is multiplexing, and how does it lead to the dramatically lower costs that this study seems to show?
So if you have a road, and normally, let's say I'm an owner of a car company, I just make cars. So you have a highway, every car that goes on that highway is mine. So if you look at the cars, you'll see that all these cars, regardless of their color and their body type, belong to my company, in this case, my genome. Now, if we have a tag on the car, the license plate, then we could have Tom's cars, Raymond's cars, Miten's cars on the same road, and the license plate can tell you which cars belong to Tom, which cars belong to Raymond, and which cars belong to Miten. The traffic does not change. The amount of cars going at any point is the same, but in one case, every car belongs to me, so it's a full amount of data corresponding to one person. In the other case, same amount of data corresponding to three people. And we could have license plates for, obviously, like we do, for hundreds to millions of people, and everyone has a car. So that's kind of the multiplexing assay. You have sequencing happening on DNA molecules from one person or multiple people, but each of individual has their DNA molecules tagged with something that tells in post-processing where the molecule came from.
That's a nice one. I like that. And I was going to say, because whenever you're taking somebody through the steps of this technology, everybody starts by assuming, and you go ahead and the way you explain it is like, oh yeah, you take one person's sample, you run it through the machine, and all of the DNA molecules in there are that person, so you understand what's going on. But really, that would be like saying, hey, we need to charge one person for their tolls, and so we're going to build a separate lane just for all of Miten's cars, and he's going to go on those. What we're really going to do is build a bunch of lanes and use all of them at once, and have each of the cars tagged with your license tag. And so that's the difference there in cost. There was another one where I was going to try to talk about, so pooled samples and being able to tag these things is important. And that time-seq, that is tagmentation indexing by methylation sequence. So they get tagmentation and methylation in there.
And the key thing I think that you've added is, yes, this notion of tagmentation. We can tag the methylated genome in such a way that we can recognize what they are and process them much more efficiently. Is that a top level way of understanding it?
Yeah. And let me interrupt you just to throw in the other bit. are you running it for a lot or a few people?
Mm-hmm.
The idea that you've got to wait to fill up your pool to do things is harder to do when you're doing individual direct to consumer things with a customer flow of dozens. It's a lot easier to do when we're looking at maybe different kinds of medical tests, but for sure at insurance where they regularly process thousands of people in a week. And so we
Yeah.
can fill up our frames and go and be very responsive. And so that's one thing that really helps us that scale. The
Cool.
other thing is, are you looking at just a few markers for each person, even
Yeah.
dozens, or are you looking at all of them? And those are the two
Yeah.
extremes. And sometimes we want to do one, and sometimes we want to do the other. Are we doing research to find new and interesting stuff? We want to look at all
Mm-hmm.
of them. Are we looking at just a few because we want to run tens of thousands of these and do them cheaply and get
Yep.
some packaged answers? Sometimes, yeah. But
Yeah.
we have strategies where we can kind of do both, which I think is
Mm-hmm.
one of
Yep.
the points.
And
Yeah.
specifically for this study, if I'm understanding, excuse me, Miten, but if I understand the study correctly, yeah, what they did is they looked more narrowly at a smaller range of markers,
Yeah.
a smaller scope, smaller coverage, whatever word you use, such that they could be much more efficient. Is that right?
Yeah.
Yeah, I think they were looking at
Yeah.
thousands,
Mm-hmm.
maybe even tens of thousands,
Yeah.
or maybe 10,000. And that's not bad. And you get some good answers, but you don't get
Measures.
all of the answers. So that's good to know.
Yeah.
Yeah. Miten, I
It,
interrupted you.
it,
Is something you want to
No,
say?
not at all. It's almost like a 2 by 2 matrix. If you think of low and high on both axes, and you have on one case the number of people, the other is number of features, and you never want to be on the bottom left. You ideally want to be on the top right. And generally speaking, the scientists and the research side of things will always be, I'd rather have some people with more data compared to more people with some data. But that left high quadrant where some people, lots of people with some data is where, okay, I may, and I think people will define it differently. Some people will say it's a definitive statement that I can look at 10,000 or 5,000 markers and get a very definitive correlated prediction based on these data. And they may be right. But I think there's two parts to it. One, of course, you can do it. You will get a measure, and it's quite strong. To me, it's a very strongly suggestive evidence. Would I say I'll hang my hat on? It's a strongly suggestive evidence. It's done deal. We just need to worry about these. Nothing else matters. Let's move on. Perhaps no. It's a useful strategy to be mindful of. It's a diagnostic evidence. It's a good place to begin. The reality is, even if this is the only piece that matters, until we've established the other piece that, okay, we actually did check through a cohort over time, which just can and does and will happen, then we know what the definitive markers are. But regardless of that, to be fair to give the authors their credit, doing this study at the scale with the markers and showing the correlation across models in human and animals and having a correlation that seems to match, it is not an exercise of we kept looking for a pattern until we found one, but more, the pattern we looked at did seem to have concordance across these species. So while it's not comprehensive, it's not just a random coincidence. There is something to it.
Good.
And
Good.
that's a great point too, that, we're not just in the business of running tests, we're in the business of coming up with new and better tests. And to
Yeah.
do that, you've got to look widely and then pare it down to run them for your everyday stuff. And how you pare that down, or how you even pick the markers to do in the first place, there are some interesting tricks you can do. And up until
Yep.
very recently, we were the only people using systems biology to try to pick our marker sets, so that we would say, hey, let's look in places where we know it's going to tell us something interesting about cancer,
Mm-hmm.
or something interesting about heart disease, or something interesting about metabolic syndrome, so we can figure out things related to those specific pieces. Not just let's look at everything and look for patterns, which is, a valid way to get started, but being able to come down and get more information out of less markers is what you really want to be able to do. You want to find the best definitive markers, not just
Yeah.
for cheapness, but for quality of information.
Mm-hmm.
Great. So these guys did this study. They were very effective in their multiplexing and their scoping and their coverage, and they got much lower prices, which is fantastic. But as you mentioned, they did a lot of their studies. They did some on humans, which is great. But I would say most of the study is actually for mice and other animals. Should we be concerned about that? Or is there a big step to kind of take this to a human application because they did so much on mice and other beasts?
I think that was a great way to kind of touch their bases, showing that they had a good technology that worked and could scale up and do it cheaply, because it's a lot cheaper to get mouse samples than it is to get human samples. So just on the front end. And so I thought that was nice. I thought that running it on humans, they did a nice job and showed that they even claimed that they had some of the best correlations out of all the methods of looking at aging clocks. And, I think you can kind of thrash around with the statistics and talk about what's better or worse. But no, I mean, I think it could be ready for prime time for humans.
Yeah, it seemed that way. And yes, I was truly impressed that they said that their predictors benchmarked favorably against all the more detailed, much more expensive approaches that we use today. So I thought that was very, very favorable. I guess a related question to that is, well, how long? I mean, how long is it going to be before we start seeing prices like this charged by different companies?
I think some of this is like who sets up the infrastructure and can do this at scale, and who are the people who are driving the scale and need, who are the customers. And of course, our answer is insurance. And that's pretty easy to say. So the other thing is, it's like nobody wants to set up a time seek factory to do this, because everybody suspects in not another 6 months, but in another year or two, there will be another even cheaper way out to do this. And in fact, I don't know if you guys want to take a couple of swings at this. Whenever you look at what they did, I thought it was fantastic, but could it be improved? Oh my God, yes. So
talk about that. So what do you think?
Well, appropriately, they were doing this for a large number of samples because they wanted to bring the price down. Could you do something where you could even do smaller samples in a more timely way? Yes. Could you do something where you would have not just one person manually running it? Could you automate it? And I think if you automated it, you could do a lot more samples. You could do them in a more timely way, but you could bring the price down even further. So instead of having what they were talking about, $6 per sample-ish for humans for 1,000 samples, you could have $6 per sample for 10,000 samples in an automated way. But that presupposes you've got this huge pipeline coming in where somebody wants to pay that and do it again and again and again, because you don't want to set up and do it once. And let me be clear, I'm not criticizing them for not doing that. They were doing it as a one-off, a first thing to show, look what we can do.
Sure.
Yeah, I agree with Raymond that there's who sets it up is very important. And what they've shown, most importantly, is that it can be done. It's not that it can be done by everyone right now or everywhere or every company, every provider, but the bottom line is this can be done. And that's the message I take from that yes, there is a way to do this. There might be optimizations that one needs to do. There's infrastructure costs, and a $6 test does not mean it's $6 to actually do it. There's obviously all the other costs, infrastructure aside, and the insurance aspects and consumer outreach context to that. But within reason, this is saying that if you are in single digit numbers for the cost, then a low to mid double digit test to consumer is feasible. Now, does it arrive tomorrow? Not likely. But will it take 10 years? Also not likely. It's more, we are closer in the few months to low number of years range than we are, it'll happen in half a decade to 10 years. So it's a strong start. But we have to be mindful that it's, at the end of the day, a technical benchmark using a research study. So amazing work.
Yep.
But there's somebody from the vet, as anybody would tell you, it's a very different thing to go from research to actually making a commercialized assay.
Absolutely. But one of my favorite sayings is the best way to predict the future is to create the future. and I think we might be in the process of doing that. And I think that's what I hear you saying, I hear you saying. So let me get out there and then you guys can beat me back. But here's my kind of out there thought. that yes, there are techniques available today that can allow us to get costs down to extremely low levels if we're doing them in high volume, if we're doing them with the right level of coverage, if we're doing them with the right multiplexing. We can do this. And because insurance is exactly one of those high volume focused areas, once we hone in on exactly what predictors we're after, there is reasonable hope that we can get costs down to this level in, let's call it, a year or two if we had the right conditions. This is an indication that it can be done. And we're in a situation where it could be done well. And in a way to use it that could be effective, perhaps more than most. And to me, that's a very encouraging thought.
And I'd even go further. I'd say there's like 3 or 4 reasons that make it inevitable that this gets cheaper. So one is the general thing that we always cite, like everybody used to talk about Moore's Law. We talk about Wright's Law, the more general version. You do something over and over again, you knock off the rough corners. If something's in production, you get economies of scale that do make it cheaper and better and higher quality, and you have fewer do-overs. So that is already in the cards. One of the things that's applied to all the time is new technologies. So we're talking about doing this in the milieu of doing like a reduced representation by sulfite sequencing. All of the things that feed into making this work better and easier would also work and make it better and easier for these newer short read technologies, these new long read technologies like nanopore, which have their own economies of scale that would act up on it. The tagmentation thing could be fine-tuned. There's a technical deal about you put these enzymes on a bead that attach to these loops of DNA, and so you get these 200 to 300 base pair DNA. That's great, and that works. We could go ahead and tune that so you have longer pieces of DNA that work with longer reads, and that would all be good. So all of these pieces would be new and better ways to do it. And I was going to add, whenever you do your enrichment to pick for the specific probes, new and better ways to do that. So we're turning the crank on 4 or 5 different areas to make it better and cheaper, and they are compatible across technologies. So we will see this be better and cheaper.
Absolutely. But to be clear, these guys got these cost reductions with, sampling sizes in the thousands, not the 10,000s, not the 100,000s, not the millions. So
Yes.
while absolutely at a population scale, epigenetics has an opportunity to become cheaper still than what they've already done in this important study.
Yes.
Great.
Yeah, maybe
guys,
we
thanks
don't
very
get
much.
it
Appreciate your intuitions on this. Anything else either of you wants to say on this?
No, I'm just still looking forward. The more people we have with more data, the more useful this becomes, not just for understanding research pieces around health and mechanisms of disease, but around being able to stop it, being able to figure out where our good exceptions are, our health superheroes who get over things better, being able to make drugs and procedures and rate different interventions. So this becomes something that I think democratizes really well the more data that we have, and that's why we're all interested in it, right?
Yeah.
Absolutely.
Yes.
Absolutely. Guys, thanks so much for your insights.
Thanks.